In this video, we are going to explain small signal equivalent circuit model of a MOSFET in which source is not connected to the body or substrate. In many applications, the source terminal is connected to the substrate terminal or body terminal B, which results in the PN junction between the source and the induced channel having a constant zero bias. In such a case, the substrate does not affect in the circuit operation and its existence can be ignored altogether. In order to maintain the cutoff condition for all the substrate to channel junctions, the substrate is usually connected to the most negative power supply in an NMOS circuit and most positive power supply in an B.M.S circuit. The resulting reverse bias voltage between the source and body, that is VSB, in an N-channel device will have an effect on the device operation. To appreciate this fact, consider an NMOS transistor shown here. Let its substrate be made negative or connected to the ground relative to the source terminal shown here. Now, the reverse bias voltage will widen this depletion region. This effect in turn reduces the channel depth. To return the channel depth to its former state, more gate to source voltage need to be applied. Now, to model the body effect, let us consider the MOSFET circuit symbol shown in figure A. Notice that the MOSFET here shown has four terminals: gate, drain, source, and the body relative to the device shown here. Figure B shows the MOSFET circuit symbol including small signal equivalent circuit model of a MOSFET with an body effect. The model includes the voltage source, bulk to source voltage source VBS, and the controlled current source GMB times VBS, where GMB is called as body transconductance. VBS is the bulk to source voltage, that is the voltage applied between bulk and as well as source terminal. This model is used for the circuit analysis whenever the source is not connected to the substrate terminal. The substrate terminal acts as a second gate or back gate for the MOSFET device. Thus, the signal VBS connected between bulk and source give rise to a drain current component GMB times VBS. If we observe this small signal equivalent circuit model with body effect, there are two current components flowing between drain and source terminal. The first current component is GMB times VBS that flows due to the bulk to source voltage applied. The second current component is GM times VGS flows due to the gate to source voltage applied between gate and source terminals. The net current is the sum of GM VGS plus GMB times VBS. The resistance shown here R0 is nothing but the resistance offered by the MOSFET between the drain and source terminal. This resistance is called as early effect resistance or channel length modulation effect resistance. This model is an extension of the hybrid pi model, but the body effect has been included in this small signal equivalent circuit model. Since the drain terminal current changed due to the bulk to source bias applied, now we can write the drain current flowing between bulk and source as GMB times VBS, or GMB equals dou ID by dou VBS, keeping VGS and VDS as constant. From this, we can define the body transconductance. The body transconductance is the change in drain current for the change in source to bulk voltage. Before we proceed further, let us recall the drain current equation in the saturation region. The drain current equation in saturation region is given by ID equals 1 by 2 Kn dash, that is process transconductance parameter times aspect ratio W by L times VGS minus VT whole square. This equation shows that the drain current ID is a function of the threshold voltage Vt as well as gate source voltage VGS. Let us consider the main component here, where we can say that the drain current is the function of the threshold voltage Vt. Proceeding further, we can write the detailed equation for the threshold voltage, including source to bulk voltage. Vt equals Vt naught plus gamma times root of 2 phi f plus source to bulk voltage minus root of 2 times phi f. Each and every parameter is defined as follows. Vt naught is the threshold voltage for the source to bulk voltage as 0. Phi f is the physical parameter with a typical value as 0.3 volt, and gamma is a fabrication process parameter whose math equation is given as gamma equals root of 2q Na epsilon s divided by cox, where q is the electron charge whose value is 1.6 into 10 to the power of minus 19 coulomb. Na is the doping concentration of the p-type substrate. Epsilon s is the permittivity of the silicon whose value is 11.7 times absolute permittivity, and COX is the oxide capacitance. Typically, gamma is a function of the voltage whose equation is given as gamma equals zero point 0.4 root of V. Now we can know that gamma GMB is related to the GM. GMB is a fraction of GM, so that we can write GMB equals X times GM, where X is given by dou Vt by dou Vsp, that is rate of change of threshold voltage by the rate of change of the source to bulk voltage. Further, the X value can be defined as gamma divided by 2 times root of 2 phi f plus Vsp. Typical value of X is in the range of 0.1 to zero point 0.3 volts. Zero point 0.3, it is not voltage. Now, this equation ID is a function of the threshold voltage. The threshold voltage is also a function of VSP. Variation of source to bulk voltage changes the threshold voltage, and in turn that changes the drain current ID. With this, we come to an end for the development of small signal equivalent circuit model of a MOSFET, where the source is not connected to the body of the MOSFET.